I will start right away by sort of making it known that I'm not a very big fan of this problem. 2.4 wants us to calculate the expectation values of x, x squared, p squared, and the resulting standard deviations of x and p for the nth stationary state of our infinite square well. The nth stationary state being this expression, which we have sort of derived earlier on in this section. The reason why I don't like this is because this is sort of very much a purely mathematical exercise and doesn't really introduce any sort of new physical insights onto our system. So because of that, this is mainly, in most cases, sort of a very big plug and chug that we sort of just, if we did not have access to an integral calculator, we would have to sort of grind our way through this bit by bit. Now, that being said, I do have access to an integral calculator. However, that isn't to say that having a certain amount of mathematical know-how is not important. So if you feel like doing these integrals, by all means, I encourage you to do so. It's a good idea to sort of have practice in how to actually do them. But for the purposes of keeping this video at a reasonable time, I will not be going over the integrals in detail. I will simply be going over the very general sort of process of solving them and then leaving them to you should you actually wish to actually do them on your own, which is something I recommend. However, I will not be doing them in detail. I'll simply be generalizing the steps that we have to do. So let's start with this first sentence and calculate all these expressions before we go on to the second part of this problem. The first thing is the expectation value of x. And as we know, the expectation value of any quantity is just taking our operator, which in this case, the operator for x is just x itself, and sandwiching it in between our complex coefficient or complex conjugated function of psi, and then the normal form of psi. However, the infinite square well psi has no imaginary terms, so as effect, we can just take the square of this and then attach an x to it in the integral. So let's do that. So this is going to be equal to, and we're going to square psi. So square root of 2 over a is just going to become 2 over a, multiplied by the integral from 0 to a, because this is where our well is defined. And then we're going to take sine squared of n times pi over a times x. And we're going to add our second operator x right behind it, dx. And from this point, the way that we would solve this is we would take advantage of the trigonometric property where we can define sine squared of any value. So sine squared of any value, let's call it y, just so that it's different from x, which we're solving in terms of here. Sine squared of y can be defined as 1/2 times the quantity of 1 minus cosine 2x. So hopefully you instantly see that if we plug this in to like this sine squared expression, then we can distribute it out and we get two integrals. One, which is just x, which is obviously a trivial integral, and then a second one, which is x times cosine of 2x. For the x times cosine of 2x one, we simply use integration by parts, defining u equal to x and dv equal to cosine 2x dx. And from that point, that is also a very trivial integral to do, I'll bet a little bit tedious. So we're not going to go through the trouble of doing all of that because that is a very long and annoying process. But as it turns out, what will happen is that these n terms will cancel each other in the final result, and this will give us a result of a over 2. Next, let's do x squared, which is the exact same process. This is just going to be equal to the exact same thing that we've defined here, with the only difference being that now instead of x, we're defining x squared. And here we do the exact same process. We start by replacing sine squared of this expression with sort of this trigonometric identity. So we use distribution property, and we distribute x squared into both of these terms. So we have two integrals now. One, which is just an integral of x squared, which is obviously trivial, and then two, which is an integral of x squared times cosine of 2x. Once again, we use integration by parts. This time, because we have an x squared instead of an x, we use it twice to get a much longer and much more tedious expression to solve. which we will not be doing here. Once again, this, once we plug into our integral calculator, gives us the quantity of a squared divided by 3 subtracted by a squared times 2 pi squared n squared. Third, let's do the expectation value of p. So p, let's write this out first. So first off, one thing that we should make a note of is that we know that p as an operator is equal to negative I h bar times the partial of whatever function we're operating on with respect to x. So because of that, what we get is that p is going to be equal to, and once again, we take the square root of 2 over a, that just gets squared as normal, so 2 over a times the integral. And here, since p has this derivative operator, our order of writing things down actually matters now. So our integral from 0 to a, and we're going to start by writing our complex conjugate expression. Thankfully, in this case, everything's very simple because the complex conjugate equals the normal expression. So we get, starting off, sine of n pi over a times x. And then we have our sandwiched operator, which is going to be this expression, negative I h bar partial with respect to x. And we're going to sandwich that in between. It's acting on psi of x, which is just sine of n pi over a times x. And we're going to close this off with a dx. So automatically, this is going to give us negative 2 over a. We're going to bring the I h bar out as well, times the integral from 0 to a. And we're going to take the derivative of this sine of x term. So that's going to give us n pi over a, which gets brought out. And then we have our sine of x, or sine of n pi over ax from earlier. That hasn't changed. And then finally our derivative term, which is going to become cosine of n pi over a x dx. If you want to solve this integral, we can just use u sub. We can u sub set u equal to sine or cosine, either one, it doesn't matter. If we use u sub, then what we get at the end is that this integral is actually going to cancel out and equal 0. Finally, the expectation value of p squared, and we're going to do the same thing. We're going to start by taking this expression and copy and pasting it because everything is mostly the same. The only difference here now is going to be our operator. So we're now applying operator p twice. So we're basically taking this expression here, negative I h bar partial with respect to x, and we're going to square it. So operator p squared is going to be equal to this thing squared. If we do that, it's going to be resulting as the two negatives make a positive, then you have two i's making a negative, so negative h bar squared. And then we're going to apply the operator on x twice, so d2 with respect to x squared, so this is going to become a second derivative in terms of x. And from here, we sort of just equate this out again. This is going to give us a sine squared integral, which is obviously, we use once again this expression of sine squared, sort of devolving it back into like a 1 and a cosine of 2x. And this is going to equal, once we sort of plug everything into our integral calculator, once again, h bar squared times n squared times pi squared over a squared. Finally, let's do the uncertainty spread. So let's start off with the standard deviation in x, and we, whoops, I'm sorry, that's a very messy sign. Okay, the standard deviation in x, and we've already learned that for any quantity, the standard deviation can be expressed as the expectation value of that value squared. So in this case, x squared subtracted by the expectation value of that value itself squared. From here, this is just going to be equal to, and we have all of our values, so expectation value of x squared is going to be this. So let's copy and paste this. And then we're subtracting it by the expectation value of x, which is a over half. Squaring it gets a squared over 4. Take the square root of everything. We can move the a squared out to get a times the square root. 1/3 minus 1/4 is just 1/12. And then we subtract it by 1 over 2 pi squared times n squared. Next, the standard deviation in p. And we know that we already calculated that the expectation value of p itself is just 0, so we can just do the square root of the expectation value of p squared. This is going to be equal to, and we have h bar squared n squared pi squared over a squared, so we just take the squared out, h bar n pi over a. And that is all of our expected quantities. Next, we want to check that the uncertainty principle is satisfied, and then we want to check which state comes closest to our uncertainty limit. So the uncertainty principle is just the idea that the product of the standard deviation of x and p has to be greater than or equal to h bar over 2. So let's start by just doing this multiplication. So the product of standard deviation of x times standard deviation in p is going to be equal to h bar times n pi, where we're sort of canceling out the a here with the a at the top here, multiplied by the square root of 1 over 12, subtracted by 1 over 2 pi squared times n squared. And from here, our goal is to get this down into a form of h bar over 2 multiplied by some constant afterwards, because that's the only way we can compare. If we sort of look at this right now, it's not entirely clear sort of whether or not this actually satisfies it. So let's try to get it into this form of h bar over 2. So we're going to start off by, let's start off by sort of combining these two fractions. So this is going to give us h bar times n times pi. And we'll take the square root, and 1 over 12 minus 1 over 2 pi squared n squared. Obviously, the common denominator here is just 12 times pi squared n squared. And then from here, at the top, we multiply by pi squared n squared, subtracted by, and we're multiplying by 6 on the other side. And from here, instantly, hopefully you see we can take the pi squared n squared out of the denominator and cancel it with the n pi over here. So this is going to be equal to just h bar times the square root of pi squared n squared minus 6 over 12. And from here, obviously, we can get the h bar over 2 by splitting up our 12 into 4 times 3, therefore giving us h bar over 2 times the square root of pi squared times n squared, subtracted by 6 over 3. And from here, our goal is to sort of get this as small as possible to see if this always satisfies the uncertainty principle. So we have pi squared n squared minus 6. N obviously goes from 1 to infinity in integer steps, so the biggest possible value we can have for this is infinity at n equals infinity. In that case, the minimum value we can get is n equals 1, which is going to give us, so at n equals 1 is going to give us the minimum value of h bar over 2 times the square root of pi squared subtracted by 6 over 3. And if we shove this into a calculator, this is going to give us h bar over 2 times 1.136. This is greater than 1, therefore this value is greater than the minimum value of h bar over 2. So as a result of that, we can say that this system does indeed satisfy the uncertainty principle, because the minimum value of the product of the standard deviation in x times the standard deviation in p is greater than h bar over 2. The minimum value is h bar over 2 multiplied by 1.136.